morning, everyone. This is Wenda. So I'm from University of Edinburgh. Today I'm going to talk about autoformalisation, which I believe is a way to bridge the gap between informal and formal proofs. So this is in collaboration with a lot of people, including Albert and Mataya Yamnik here, and many others. So first is about proof assistant. Many of you here are expert of proof assistant. Probably I don't need to say much about this slide. So in short, proof assistant is just a piece of software that can understand the mathematical definitions and the proofs, and so we can machine check our proofs in computers. Yeah, it's a very good thing, and I believe it's gaining popularities within the math community. So one of the major achievements recently is the liquid tensor experiment, which is led by our Johan here, and it's finished just in 2022, and 90K proofs and about 20 contributors. So this is really a demonstration that with proof assistant, we can have collaborative effort on mathematical project. And also polynomial Freeman-Rassam conjecture, and a result by by 4 big names, and it's amazing. It's a combinatoric result, and 33 pages, and amazingly finished just within 3 weeks. This is truly astonishing. And finally, we follow our beloved Kevin Buzzer, and who recently got this PTSRC fellowship in last year. We hope we can have some major milestone after 5 years. Okay, these are good. These are all good news, but still there are some drawbacks with our proof assistant. So first is about, so this is one of the tweets on Twitter saying, okay, this is just a snapshot, I believe it's from Cork. So, and then it's kind of, it's good, but still it's not legible, and we cannot comprehend this kind of proof without running it in a proof assistant. And it's not the way we communicate our mathematics, and it's also not very good for maintenance, or like also for like new beginners. So there's a quite steep learning curve with our existing proof assistant. And also, like we still need a lot of effort to formalize our mathematical result. For example, in Cork, we have this wonderful odd order theorem, 6 years, 250 pages of informal proof. And also, I believe in the Lin chart, there has been an estimation of how much effort to completely formalize the free math class theorem. And so I believe so it's on paper, it should be 1,000 to 5,000 pages, including the background series. And on average, I believe there's a ratio, so like 2,000 lines of link code per page. So I believe, according to Kevin Buzzer on Zurich, I believe there's 100 person years effort to formalize this Feynman theorem. And also, I believe people on the Zurich chart are talking about the STAX project, which is 7,000 pages. So the question we now have is, can we formalize at the speed of new papers appear on the archive? So before going further, we can just have a bird's eye view of our formalization process. First, right now, I don't think we have that super intelligent AI yet. So to formalize, we first need our humans to read the papers carefully. And it's usually not just one, just all the dependencies, so quite a few papers. And then with humans, we understand this paper, and then we convert it into our formal proofs like this. And then usually we are not simply communicating our mathematical ideas through formal ideas through these formal proofs. They are just maybe too detailed. And so for the communication, we also need to write a paper about our formalization effort. Yeah, so it's kind of process of informalization, and then we communicate through also in natural language. So you see there's a word of formal and there's a word of informal, and it's our humans, our brains. So we are the one who try to bridge the gap between these two words. So really we want some maybe more automatic method to bridge this gap. So there are already some earlier effort. So one is, so there's an effort to do using neural natural language method, translation method between MISA and LaTeX, which is done by Silary Kalisik and our Joseph Urban here. And so in this 2020 paper, so they first coined the term autoformalisation. And in this paper, although I believe Joseph has explored
Autoformalisation is still like 2014, very close to 2020.
Okay, yeah, okay. Yeah, thanks for the correction. Yeah, so it's kind of the first paper I read, so probably I missed some of the history here. Yeah, so in this paper, they have explored this unsupervised machine translation. Is kind of a technique. We don't really need a parallel corpus, and then we can just try to pair these informal and formal sentences. Although in this paper they have explored, but the performance is still inferior in comparison to supervised approach. So really, so we still need parallel corpus, or at least related corpus, which means we need to manually have informal sentence and formal sentence together, quite a few of them, in order to have a reasonable, good performance neural model. Yeah, so that is one of the first effort. And also there's quite some effort in controlled natural language proofs. So again here we have Peter, so this approach in Isabel, and yes, quite good. And also by Patrick Massel in Lean, I believe there's a verbose Lean effort. And also there are many more like GF and STEX, which is something I really don't know before I come here. So again, thanks. So the question here, I believe, is still they are maybe a little bit too controlled, and then our humans need to first guess the syntax of the formal and the informal, and then we manually type down some symbolic rules before we can pass between these two sentences. And so this kind of inflexible, and then again some human effort is needed. But I think they are good things, so they will be complementary to what I'm going to talk about next. Yeah, so these are the interface of an approach and the verbose link. Okay, so what I'm mainly going to talk about today is about the so-called large language model. I know it's a buzzword. It has a lot of good functionalities, but it is, again, not perfect. So there's a lot of drawbacks. So just we can be critical about these kind of techniques. So large language models like ChatGPT, Llama, and Gemini, it's just a neural model that generative model the distribution of sentences. It's a generative model, and unsupervised just trained on almost all this data on the internet. So unlike previous models where we have one model for one task, so this is really a generic model that is just one model that can be used for a lot of tasks. And it has a technique called, maybe some phenomena that is only like demonstrate or it's available in these large models is so-called in-context learning, where it's kind of we can quickly adapt the behavior of large language models without changing its weight. We can just have some demonstrations in the context before our task. And so the model can quickly learn to do some other tasks just by a few examples without changing its weight. So it's quite similar to humans, where we can learn to drive just by some demonstrations without, so we are not a baby. So it's quite amazing. Yeah, so our hope here is because large language model, they can do a lot of tasks, so we hope it can somehow automatically translate between informal and formal sentences. So the question we have before playing around large language models is that can off-the-shelf large language models translate between informal and formal sentences without an aligned corpus? So the aligned corpus is really, I believe, is a main bottleneck for the bridge here. So before the era of large language models, we have machine translation, neural machine translations, but it really requires paired sentences between two languages. So, but here with large language models, I think the good thing we really find is that it does not require this aligned corpus, and it just can have some not too bad performance with few short demonstrations. Yeah, so in our first paper with language models, we have some examples on the mini F2F data set. So it's really a collection of problems, competition level, high school problems, not too hard, but it's just good for benchmarking. So on the left is a question that proves that there's no function f from the set of non-negative integers into itself, such that ffn is equal to m plus 1987 for every n. Yeah, so it's a natural language sentence. And so we prompt the model, and it can give us it's a formalization in Isabel, which looks good to me. And also on the right, so it's some more practical problems. So with all the girls at the Madeline school line up in a row of 8, so there are 7 left over. So instead, they line up in rows of 4. How many are left over? So the final answer is 3. So then we try to translate into Isabel. So then the result is here. Also, yeah, looks not too bad. So in general, so this mini F2F dataset have 500 problems, and then we use 150 as a test set, and so we manually check the performance, and in the end, I believe 38 of them are good to me. So, but there are still some problems, some failures with this large language model formalization. So the major problem to me is sometimes it has hard time to align definitions. So as can be seen on the left, so which is let f to be a linear function, and then but here when translating this into a formal statement, and it kind of hallucinates a predicate of linear, which is reasonable, but in Isabel, at least in the standard library, we really don't have this predicate linear. So it's kind of hallucinate. And also on the right, so the question is, we want to formalize the proposition that an arbitrary product of compact spaces is compact. Yeah, and again, I believe maybe it's possible in Lean, so where we might have this compact space like on some type classes, so that we can directly use the product operator. But again, in either way, we have a dedicated predicate or operations for this called compact space product topology, which we use to multiply like a set of topological spaces together. So rather than just use product like as an overloaded operation, so we have a dedicated operation. Again, so this model is using a wrong definition. And also another observation is that the informalization is easier than formalization, which is understandable because, again, the formal statement is more precise and has more details. So on the left is, again, so if A and B are sets such that A is a subset of B and the B is a subset of A, and then A equals B. So formal to informal looks good to me. And also on the right is really the definition of topology here, and it translated with reasonable quality.
So this is done purely with an LLM?
Yes, purely with LM. And just with like 4 demonstrations. You can find the details in our paper. So we don't have an aligned corpus. We don't have these informal to formal pairs. So just several demonstrations, and so this is what can be achieved with Codex, which is actually a model 2 years ago. So right now, I believe the model is only going to be better.
I'd love to have Codex explain its reasoning, because why does it know that is open can be elided everywhere?
Yeah.
How did you learn that? How do you know?
Yeah. There's a lot of information on the internet. So as humans, we cannot read all of them, but as a model, so somehow it has the knowledge.
So this example also uses finite intersection instead of binary intersection. And it's also sort of accords with like what I've seen with some of the failure modes that like, well, if you say something wrong in the lemma or you say something weird in the lemma, it'll just ignore that and write what it's on the text.
Yes.
Like it knows a statement about topology,
Yeah.
right? And it's like, I see open, I think it's
Yes.
defining the topology.
Yeah. I think so. Yeah.
Topology, it finds the
It's basically regurgitating stolen text.
Yeah, it really has some bugs.
Don't we all? Sometimes.
Yeah.
So if you just write topology and then you write anything under that, so it might give the same result because it finds the definition of topology somewhere. Does it look at the
To find out
the
what
other
it
lines?
is.
Yeah, basically,
What it's
So it
about.
gives probably you want the definition of a topology. Here it is.
Yeah, I think that's worth trying. So I think if there's something minor, it's just autocorrect because it has some prior knowledge. But if it's something major, I think it still will be faithful.
Have you tried just doing slight variations of this that are wrong?
Yeah, again, I think if the variation is not too big, I think it can fix it in an automatic way. But if there's something major, I think it will just do it faithfully. So it's going to be a wrong definition. Okay, so that's our first discovery. So with large language models, we can do autoformalisation, and then there are something good and something bad. So here as a follow-up work, so we try to use informalization to help autoformalization. So our previous observation is that informalization is easier and more accurate than formalization. So yeah, and then we try to use this to improve the performance of autoformalization. So here are the some informalization result with the latest GPT-4 model. You can see in Lin and in Isabel. So yeah, they both look reasonable to me. So we believe they are reasonable, good informalization. And so in a follow-up paper, we use language models to informalize this statement to create a synthetic parallel corpus, and yeah, and also on Lin and on Isabel. So it's synthetic again. We just use this large language model again. We don't need any humans to do that, and then we fine-tune the synthetic, which is like we try to train on this synthetic data set on Isabel and on Lin, and also they combined. So finally, again, we have some improved performance. So the most interesting part in this is that, okay, we can, with this synthetic data set, we can have improved performance. And also, we find out if a model that is fine-tuned on both Lin and Isabel, it will have like better performance than Lin or than on Isabel alone. So that is something like multilingual, multi-language diversity can help. So if we have this natural language and Lin, natural language and Isabel, so it can actually learn something across formal languages. So that is something that's I think this is also a phenomenon that has been observed in machine translation, where people have tried to pre-train model on multiple languages, and then you have better performance on the target language. Here we observe similar phenomenon on formal language as well.
So in your synthetic corpus, do you have both positive and negative examples? Learning theory says we really need negative examples to do efficient learning. We can't just learn on positive examples.
I think they are mostly positive examples. Yeah, we will do some human evaluation. Turns out like 70% of them are good. So rather than just train on this. So if we do have identification of negative examples, so I believe we can have even better performance using some techniques like contrasting learning. But that could be future work. But here we are just use them as positive example.
How is the effort level measured?
That's again human. We have a rank between 1 and 5, and then humans examine each one of them and to see if how much effort do we need to correct the.
So it's a Likert scale.
Oh, I see.
Huh?
It's a Likert scale.
Yeah. Okay, so that is something about autoformalization. Okay, I briefly introduce the idea of autoformalization and how can we improve its performance using informalization. So here in the following part, I'm going to talk about some applications of autoformalization. The first application we can have is data augmentation, especially with neural cell improvers, which need to be trained on again, data. We need more data. So previously, we can only train these neural improvers supervised in a supervised way on the existing formal data, on the existing formal corpus, which is not much, tiny. And then with this idea, this technique of autoformalization, we can, without much effort, we can translate informal questions into formal ones, and then run our neural agent, proof agent on top of this auto-formalized statement. So there's an idea called expert iteration, which means that we can use neural agent to create better corpus, and then use this corpus to train better agent, and then again to have even better corpus. So there's a good cycle. So with this neural agent, we can prove more on the synthetic data, we can try to prove some of them, and then we can use the trees, the succeeded proof to train a better agent, which we can prove even more zeros. So that is the idea of SAW. So again, of our papers, so we have better performance than just sledgehammer, which is the default automation in EW. So after that, a second application of autoformalization is that we can even use informal proof to guide formal theorem proving. Yeah, so again, so we can have, so the informal proofs can either be human written or sampled from large language models. So and then here is the pipeline. So first we have this draft stage where given an formal statement. So we were benchmarking on this mini F2F dataset, which have both formal and informal statement, but not proofs. So given a formal statement, we can use large language model to sample an informal solution, or there's some informal like model answers we can use. And then we have an informal proof, and then we again use a model, large language model, again, could be, and we use it as an auto-formalizer. That is, we turn it into a so-called formal sketch. So it's almost like a formal proof, except for each step, we don't have the justification. So it's like in informal proofs where for the steps, if the gap is not too large, we just leave it implicit. We believe our human beings can bridge the gap. And so here the formal sketch is almost like formal proofs, but the sketch, you just fill it with our keyword sorry. So and finally, we use off-the-shelf ATPs to fill the gap. So in this particular paper, we were using sledgehammer, but it does not prevent us to use neural provers to bridge the gap. So this is like an example of a formal sketch. You say given a problem, informal. So here is informal statement, but in our experiment we were using the formal one, and then we have a formal informal proof, and then the bottom is just an informal a formal sketch. And so here is some gaps. We just use sorry as a placeholder for the gaps. So with this idea, we can have even better performance on the mini F2F dataset. So the most interesting part is actually this number. This is actually which means that on the validation set, so with human informal proof, like human written model answers, we can only have 42, but then with large language model sampled proof, we can have 43. So that means, okay, a sampled solution can even better guide the formal theorem proof. So the idea, the rationale here, the rationale here is that human written proofs, they are scarce. So for this, we only actually have one weight. And so sometimes the gap can be too large for the ATPs to bridge. So in that case, we consider the formal proof is a failure. But sampled solutions are cheap. We can easily sample millions of them, but in this case, we sample 100 of them. And so one of these, it just has the right gap. So the gap is just right for the ATPs to bridge. And so it has better performance here. Okay, so after a follow-up work that I have been involved in, so is we can have better sketch. So previously, the sketch is just a normal, like informal proof we would like to write on paper, but then we can ask model actually to have a slightly sub-goal-based proof, which is easier to have a formal sketch. So this is just a this is a sub-goal-based proof. It has clear steps, so which make it easier to generate a formal sketch. Okay, that's the second application. We use autoformalisation to guide formal theorem proving. So the third application is that actually, so with current large language models, it has been used for various reasoning tasks. But again, it's not very reliable. So, and we want it to be slightly more reliable. So, and so here, the idea is that we can formalize some of the reasoning, some of the steps into the proof assistant, and then to check if they are logically consistent. If they are good, okay, and then if not, so we can filter out some obviously logically inconsistent steps. So the current default approach in large language model reasoning is so-called majority vote, where we have the final answer and then sample the query large language model a few times. So if most of them agree on a certain answer, on a specific answer, and then we believe that answer is a good one. And so with autoformalisation, we can use proof assistant to figure out some obviously inconsistent wrong answers. And so the performance of majority vote improves. Yes, that's most of it. So there are some challenges. I think I'm going to talk more about these challenges in the afternoon. We have plenty of time in the afternoon. So yes, basically it has a lot of ways that we can still improve upon the current autoformalisation techniques using large language models. So to summarize, so the whole idea of using large language model is that we want to reduce the human effort when translating between informal and formal proofs. And the benefit of large language model is that it does not require an aligned corpus. So it has some applications, data augmentation, guiding formal theorem proving, and also aid informal reasonings by translating and checking some informal rationale in a formal environment. So there are some challenges which I'm going to talk about in detail this afternoon. Okay, that's all for my talk today. So.